Okay, so now in this video I'm going to tell about the data encryption standard, which is called DES. So it is a block cipher, and even though it's a block cipher, it uses both substitution and transposition repeatedly for about 16 cycles. And so the underlying principle is basically you build encryption at each layer. So you have a plain text message and you do an encryption once, and then you do again encryption, and this is like kind of a high level idea about this. And in each level of encryption, it involves both substitution and transposition. So let's see the details of the cycle. Again, we are going to first see an overview of the whole DES and then go into the details of each cycle. So we have the plain text block, which is 64 bits. So again, as I said, this is a block cipher. So the input is a block of 64 bits. So if your input is, if whatever you want to encrypt is more than 64 bits, you have to break it into multiple blocks and encrypt each block and send them separately. So the input block goes through an initial permutation. So this is what I mean by the permutation. So before that, let me just again introduce permutation. So permutation is basically kind of moving around the bits that are passed as input to what is called a P box. So the P box defines the rules for permutation. So in this case, this is a normal permutation where you pass 4 bits to the P box and you get out 4 bits out of the P box. So the bit in position 1 is moved to position 3, the bit in position 2 is moved to position 1, the bit in position 3 is moved to position 2, and the bit in position 4 comes out as the bit in position 4. Now expansion permutation is where you increase the number of bits from what you input and then from what you output. So here in this example, you pass 4 bits as input to the P box, and you get out 6 bits out of it. So the first bit comes out as it is, second bit is duplicated, comes out as the second bit as well as the fourth bit, the third bit comes out as a fifth bit, and the fourth bit comes out as both the third bit as well as the final bit. And then the permuted choice is a kind of permutation where the output, the number of bits, is less than the input. So in this example, you have 4 bits passed as input. The first and the last bits are kind of suppressed. The second bit comes out as the second bit here, and the third bit comes out as the first bit. So these are the 3 types of permutations. So what we do, the initial permutation in this DES is a kind of a normal permutation. It goes through this table like this. So the bit in position 1 is moved to position 40, the bit in position 2 is moved to 8, the bit in position 3 is moved to position 48, the bit in position 4 is moved to position 16, and so on, and the bit in position 8 is moved to position 32. Similarly, the bit in position 9 is moved to 39, the bit in position 10 is moved to 7, the bit in position 11 is moved to 47, the bit in position 12 is moved to 15, and likewise the bit in position 16 is moved to 31, and so on. So after the initial permutation, what we do is we break the kind of the block into 2 sub-halves, which is L0 and R0, and both are input to the cycle. L0 and R0 is input to the cycle, as well as there is a 64-bit key that DES uses. So again, this is a symmetric cipher, so it's the same key used at both the sender and receiver side. So the key size used by DES is 64 bits, same as the block size for the input, which is also 64 bits. So the key again is processed in a different way. So even though it's a single key that is used from the user point of view for DES, we kind of manipulate the key a little bit for each cycle, and we feed those kind of keys to the cycles. So we'll quickly see immediately after this how the keys or the bits in the key are moved around, so that you can generate 16 different keys, so that because we have 16 cycles for DES. So for a particular cycle, we feed in the key for that cycle as well as the L0, the subhalf, and the R0 subhalf. We go through some processing, which we'll see as a Feistel network processing, and what we get out is a 32-bit quantity out of the cycle. So the 32-bit quantity that comes out of a cycle after the Feistel network, after the processing, is we call it as the right half R1. So the left half output L1 is same as R0. So whatever is R0 is same as L1. So now L1 and R1 are fed to the next cycle as well as the key for that cycle 2. So then what you get out is R2, and L2 is same as R1. So basically in any cycle, say cycle I, we feed in Li minus 1 and Ri minus 1 and the key Ki for that cycle. What you get out is the Ri, the 32-bit portion output of the cycle, which is now the right half output. The left half Li is going to be Ri minus 1. So likewise here for cycle 16, we feed in L15 and R15 to the cycle and the 64-bit key for that cycle, and what we get out is R16, the 32-bit subhalf, the right half, and the L16 is simply R15. So at the end of cycle 16, we kind of combine the L16 and R16, so each is 32-bit, so when they are put together it is 64-bit. It goes through a final permutation, and the final permutation is according to this table. So here the bit in position 1 goes to 58, the bit in position 2 goes to 50, and then to 42, 34, 26, 18, 10, and then it goes to position 2. So that is bit in position 8 goes to position 2, and the bit in position 9 goes to position 60, the bit in position 10 goes to 52, and so on. Okay, so that's how the bits are moved around, and after the final permutation, what we get out is a 64-bit ciphertext. So as far as DES is concerned, we have a 64-bit plain text and a 64-bit key. So it's a plain text block, so block cipher, and what we get out is a 64-bit ciphertext block. So now what happens inside each cycle as far as encryption is concerned, that's what we're going to see now. So as I said, for each cycle, you start with the same key that is known to the user as a 64-bit key, and then we do some processing that is specific for each cycle. So what we do initially is we remove every 8th bit in the key, which is the same for every cycle. So when you remove every 8th bit in the key, it's like this. So you have a 64-bit key. We remove every 8th bit, so we remove this bit. So this is some key I just came up with, and I removed the 8th bit in position 16, 24, 32, 40, 48, 56, and 64. So which means the 64-bit key essentially reduces to a 56-bit key because you removed 8 bits now when you removed every 8th bit. So those 56 bits of the key are broken into two halves. So 56 bits when you break, it's like 28 bit and then another 28 bits. So these are the first 28 bits and these are the next 28 bits. Now these two 28-bit halves go through some shifting, okay, left shifting. So how many bits we shift to the left depends on the cycle, okay. So if you're going to use the key for cycle 1, we move the bits in both the 28-bit subhalves by 1 bit position to the left. Same thing for cycle 2, but for cycle 3 we move the bits 2 bits to the left for each of the subhalves. So let's see, if this is cycle 1, this is before you move around, so this is you move to the left by 1 bit. So this 0 goes all the way, it wraps around and goes to this position. This one moves left 1 bit to the left, it's here. This 0 moves 1 bit to the left, it is here. These two ones move 1 bit to the left, so these are 1 1. Then these two zeros move 1 bit to the left, so 0 0. So this one actually moves 1 bit to the left, this 0 goes 1 bit to the left, and 1 goes 1 bit to the left, and so on. So same thing happens in this second half. So this one gets wrapped around and goes here. This one moves 1 bit to the left, it is here. This 0 moves 1 bit to the left, it's here. These two ones shift 1 bit to the left and they are here. So that's what is basically shifting. So once they shift, as they show here, so the keys are shifted, and then it is goes to a permuted choice kind of permutation where the 56 bits are reduced to 48 bits. So what happens is this. So that permutation happens like this. So the 56 bits are reduced to 48 bits according to let me show you the table for that. Okay, so this is a choice permutation that reduces the 56 bits to 48 bits. So naturally what happens when you want to reduce from 56 bits to 48 bits, some of the bits have to be suppressed and the other bits are moved around. So the bit in position 1 is moved to position 5, the bit in position 2 is moved to position 24, the bit in position 3 is moved to 7, and so on. The bit in position 9 is kind of suppressed, the bits in position 22, 25, 35, 38 and all, they are all suppressed. So essentially we lose 8 bits, and what we get out of this key processing is a 48-bit key. So what gets in is a 48-bit key. Now we have the two halves, the left half which is 32-bit, the right half which is 32-bit. So we take the right half first and feed it through the Feistel network. So the Feistel network takes Ri minus 1 and this Ki. So this is like the black box for the Feistel network. Okay, so what is the input to the Feistel network is Ri minus 1 and Ki for cycle I. And so what happens is this. So the 32-bit right half goes to an expansion permutation, and we make it a 48-bit quantity. So we want to expand from 32 bits to 48 bits. So that's an expansion permutation. So the bits in position 1, the bit in position 1 is moved to positions 2 and 48. The bit in position 2 is moved to 3. The bit in position 3 is moved to 4. The bit in position 4 is moved to 5 and 7. The bit in position 5 is moved to position 6 and 8. So we're basically increasing the number of bits from 32 bits to 48 bits. So once we have an expansion permutation, we do a simple XOR operation of these 48 bits with the 48 bits of the key. So it's a simple bit by bit XOR operation. So after the XOR operation, what comes out here is also 48 bits. Now these 48 bits go through two things. One is a substitution process. So the 48 bits after the substitution process comes out as 48 bits, but then we further process them through a permuted choice permutation and reduce them to 32 bits. So let's first see the substitution operation for this 48 bits, and for that we use what is called the S boxes. So let me illustrate with an example here. So you have a 48-bit input. Okay, so the 48-bit input goes through a substitution as well as a permuted choice together, and so that's what we call it as substitution with permutation, and what comes out is a 32-bit output. So what happens here? So we break it down into 6-bit quantities. So 48 bits, so the first 6 bits is one kind of sub block, and then the next 6 bits and next 6 bits and so on. So if you break the 48 bits in with 6 bits per sub block, we'll have 8 blocks. So we'll have them pass through S box 1, S box 2, X box 3 and so on up to X box 8. So the X boxes look like this. So what happens is this. So we have the 6-bit input. So for example, you have 0, 1, 1, 1, 0, 1. That's the first 6-bit input. We take the 0, we basically take the leftmost bit and the rightmost bit. So this is the leftmost bit, which is a 0, and the rightmost bit, which is a 1. So 0 and 1 in binary, if you convert that to decimal, it is 1. And then we have this second to 5th bit, which is 1 1 1 0. So 1 1 1 0 in decimal, it's going to be 14, because this is like 1 is actually 0, this is 2 plus 4 plus 8, which is 14. So what we now do is we take this row value and the column, we take this as a row index and the column index for S box 1. So we index into row 1 of S box 1 and index into column 14 of S box 1. So row 1 here and column 14 here is basically the value is 3. So the values here will also range from 0 to 15. So we index into row 1 here and column 14 here, that is 3. So I'm going to write that's the Xbox result, and 3 I'm going to write as a 4-bit quantity because the values are from 0 to 15 what comes out of the S boxes. So we can write the 3 as 0011. Okay, now the next S box we have bits in position 7, 8, 9, 10, 11 and 12. So that is 0, 1, 0, 0, 1, 0. So that is 0, 1, 0, 0, 1, 0. So similarly we group the first and the last bits together, so that will be 0 and 0, and then the second, third, fourth and the fifth bit together, that will be 1, 0, 0, 1. So 1, 0, 0, 1 in decimal is going to be 1, 2, 4, 8. So 8 plus 1 is 9. So we index into S box 2 with row index value 0 and column index value 9. So the row index value is 0 for X box 2 and the column index value is 9. What we get out is 7. So this is the result, and I can write 7 in binary as 0, 1, 1, 1. So same thing, we repeat, continue. Now the third set of bits 13 to 18. 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1. So 1 and 1 together, the first and the last bit together is 1, 1. That is 3 in decimal. And then 1, 0, 1, 0, the middle bits, which is 10. 1, 2, 4, 8. 2 plus 8 is 10. So we basically now index into Xbox 3. Xbox 3 we index into row 3 and column 10. So this is row 3 and column 10. That's going to be 14. So what we get out is 14, and that is in binary 1, 1, 1, 0. Okay. So we group all these 4-bit outputs together. That will make 32 bits because we have 8 S boxes. So 4-bit per S box. It is like 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 0 here, and then 0, 1, 1, 0 and so on. So just for clarification, for people who are not familiar decimal to binary conversion, so the exponents of 2 are like 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8 and so on. So if I want to write 12 in binary, I try to accommodate as much as possible. I go from left to right, so I can accommodate 8 within 12, so I put a 1 there, so the remaining is 4, right? So 4 has to be 1, 0, 0, right? So 12 is 1, 1, 0, 0, whereas 5 I cannot accommodate, which is an 8, so I put a 0, but 4 I can accommodate within 5, so I put a 1. I cannot accommodate 0 with, the remaining is 1. I cannot accommodate 2 within 1, so it is 0, and then the remaining is 1. 9 I can put a 1 here for 8 because it is 8 is less than 9, and the remaining is 1, so I cannot put a 1 for 4 or 2, so I put 0, 0, and that is 1. So same thing with 3. Let's say I cannot put a 1 here because 8 is greater than 3, so I have to put a 0. Similarly for 4 I cannot put a 1 because 4 is greater than 3, so I have to put a 1 here. So we have accounted for 2 and the remaining is 1, so I put a 1 here. So that's how I convert from decimal to binary. Alright, so what we do now is, what we get out of the S box is a 32-bit quantity. So S box is substitution long is permuted choice. We get a 32-bit output, and that goes through a permutation, and that permutation is according to, again, this P box table. So this is a 32-bit normal input, and the bits get permuted. It's a 1-to-1 mapping. The bit in position 1 goes to position 9, the bit in position 2 goes to 17, the bit in position 3 goes to 23, the bit in position 4 goes to 31. So likewise, the bit in position 8 goes to position 18, and so on. Okay, so that's a normal permutation. So out after this, it comes as a 32-bit quantity. So I can do an XOR of that 32-bit quantity with this left data half, Li minus 1. So you're looking at cycle I. So you do an XOR of this 32 bits and the XOR of what comes out of the Feistel network. And the XOR operation also gives back you the 32-bit quantity, which is now your right data half for the next that comes out of cycle I. So this is your Ri, and so basically Ri is this Li minus 1 XORed with this Feistel network output, because that comes out of the Feistel network. So what is fed to the Feistel network is Ri minus 1 and this Ki. Okay, so an Li is simply, it is coming from Ri minus 1. So this is what summarizes the encryption process for DES. So Li is simply Ri minus 1. Okay, and so Li is simply Ri minus 1, and Ri is simply Li minus 1 XORed with the output of the Feistel network, and the output of the Feistel network is Ri minus 1 and the key Ki, or the input, and what it comes out of this whole processing, whatever comes out of after passing in Ri minus 1 and Ki and going through all this process for the Feistel network, whatever comes out here is XORed with Li minus 1 to get our Ri. Okay. Now the decryption process in DES is very simple, is the same as almost encryption. The only difference is like this: we go from backwards rather than going from cycle 1 2 3 4. We go from the backward. Okay, now this is what we just saw. This is for encryption. We said Lj or Li, say here I refer to the cycles as J. So Lj is simply Rj minus 1. So if you go back and look at the cycle, Lj or Li is simply the previous right half, which is Ri minus 1 or Rj minus 1, and the right half Rj or Ri is Li minus 1 XORed with the Feistel network output, which is basically taking Ri minus 1 and K as input and giving a 32-bit output. Now decryption will make use of this, as I'll show here. So in decryption is the opposite, so which means like this. So for a cycle I am going to pass Li and Ri as input, and what I want to get out is Li minus 1 and Ri minus 1. So for decryption, I want to pass Li and Ri as input, and what I want to get out is Li minus 1 and Ri minus 1. So how to do that? So essentially what I have here is, you can see now Lj is same as Rj minus 1. So you just switch them, so it makes it Rj minus 1 same as Lj. Because if Lj is equal to Rj minus 1, Rj minus 1 is same as Lj. Now I want to get this Lj minus 1. Remember, you want to get this Li minus 1 here. So to get this, we make use of the XOR property. Lj minus 1 is Rj XORed with this Feistel network output f of Rj minus 1 and Kj. But we know that Rj minus 1 is nothing but Lj. So that is, now we know, because when we do decryption, we know Lj and Rj. We want to get Lj minus 1 and Rj minus 1. So since Rj minus 1 is same as Lj, we can use Lj and pass that to the Feistel network. So that's what I show here. I pass this Lj, which is Rj minus 1 or Ri minus 1, to the Feistel network. These things go through the same kind of processing for the keys. So depending on your cycle 16, you go through that kind of processing, cycle 15, that particular kind of processing. What happens in the Feistel network is the same for both encryption and decryption. So that's kind of the specialty of DES. Okay, so what we get out is a 32-bit quantity. We XOR that with this Ri or Rj, and what we get out is Li minus 1. So we can do this XOR of Ri with Li with what comes out as the Feistel network. Okay, and that will get you Li minus 1. So this is a very interesting thing in DES. Both encryption as well as the decryption are the same. Okay. So we'll stop here and then we'll continue in another video.